This is lesson 8.4, the pH scale. So to calculate the pH of a solution, you're going to use the following formula. The pH is always equal to the negative log of the concentration of H+. So, vice versa, if you're trying to find the concentration of H+ and you only know the pH, you can use the formula, the concentration of H+ is equal to 10 to the negative pH. For example, if the concentration of H+ is 0.1 molar, really that means the concentration of H+ is 10 to the negative 1, which means the pH must be 1. Here's another. If the concentration of H+ is 0.01, that's really 10 to the negative 2, which means the pH equals 2. The pH scale is always positive and has no units. It goes from 0 to 14, with 0 being the most acidic and 14 being the most basic. pH is inversely related to the concentration of H+. So as your concentration of acid goes up, your pH goes down. And finally, the change in one pH unit is equal to a 10-fold change in the concentration of H+, as we saw in the previous example. Now, to measure pH, we use a pH meter. A pH meter reads the concentration of H+ with an electrode to several decimal points, and this is what we are using when we use the vernier pH probes. Now, also important when you're calculating pH is the ionization of water. So really water is continuously ionizing into H+ ions and OH- ions, and this is a reversible equilibrium, so it's always occurring. And we have a special equilibrium constant that we call Kw for the ionic product constant of water. So Kw is equal to H+ times OH-. And remember, we don't put liquids into our Kw expression, so we leave out the H2O liquid. And Kw at 25 degrees Celsius is always equal to 1 times 10 to the negative 14th. So it's always a constant at room temperature. So if we know that Kw is always a constant at room temperature, then we can calculate the concentration of OH- or the concentration of H+ if we're given one or the other. Now, Kw is temperature dependent, meaning that it changes with temperature, because remember, equilibrium constants can change with temperature, and Kw is endothermic, so energy is on the left side of this equation for the autoionization of water. Here's an example using Kw. A sample of blood at 25 degrees Celsius has a concentration of H+ equal to 4.6 times 10 to the negative 8th molar. Calculate the concentration of OH- and state whether the blood is acidic, neutral, or basic. How would you expect its pH to be altered at body temperature, which is higher at 37 degrees Celsius? So, to do this problem, we know that Kw equals the concentration of H+ times the concentration of OH-, and that at 25 degrees Celsius, this is a constant. So the constant is 1 times 10 to the negative 14th. We know the concentration of H+, 4.6 times 10 to the negative 8th, and so we can solve for the concentration of OH-. So when we divide both sides by the concentration of H+, we get the concentration of OH- equals 2.17 times 10 to the negative 7 moles per decimeter cube. Now the question asks whether it's acidic, neutral, or basic, and we could go back and find the pH based on the concentration of H+, or you can just compare. The concentration of OH- is greater than the concentration of H+, which means the solution must be basic, or the blood must be basic. Now, if you raise the temperature, remember this is an endothermic reaction, so as you raise the temperature, the Kw will increase because you will shift the reaction to the right. Therefore, the pH will decrease, meaning go down. Just like we had pH, we can also find something called POH, which is equal to the negative log of the concentration of OH minus. So just like pH, if we know the concentration of OH minus, if we know the POH, we can find the concentration of OH minus by taking 10 to the negative POH. Conveniently, the pH plus the POH in a solution at 25 degrees is equal to 14, similar to Kw. And last but not least, we have more P's. We have the pKw. So if the pKw is equal to the negative log of Kw, and so Kw is equal to 10 to the negative pKw. And we'll see where this comes into play a little bit later on. So for strong acids and strong bases, you can calculate the pH and the POH directly from the initial concentrations, because for strong acids and strong bases, they're completely dissociated, meaning that there's no acid or base left remaining when they're dissolved in aqueous solution. So here's an example of a pH calculation for strong acids and strong bases. Calculate the pH of the following at 298 kelvins. So you have 0.1 molar NaOH, which is a strong base, and you have 0.15 molar sulfuric acid, which is a strong acid. So let's start with NaOH. We know that in NaOH we have OH minus ions. So we can find the POH, which is equal to the negative log of the concentration of OH minus. And since it's a strong base, the concentration of OH minus is just 0.1 molar. And so the POH, when you plug this in, is equal to 1. And remember, POH plus pH has to equal 14, so the pH must be 13. To find the pH of sulfuric acid, we know we're going to use the negative log of H+, because sulfuric acid contains H+. And to find the concentration of H+, we know there's 2 H's for every sulfuric acid. So 0.15 times 2 gives us a concentration of 0.3 molar for H+. So when we plug this into our formula, we get a pH equal to 0.52, which is a very strong acid, a very low pH. Remember from topic 1 that titrations are often used to find the concentration of a solution that we don't know. So you can titrate a strong acid and a strong base together if you don't know the concentration of your acid or you don't know the concentration of your base, but you do know the concentration of the other. Now, the equivalence point of the titration is going to be the point where the strong acid exactly neutralizes the strong base, so they're in equilibrium, equal amounts of acid and base. Standardization is the calculation of the exact concentration of one solution when the other is known. So this again is another word for when we're finding the concentration of a solution that we don't know. So when you titrate a strong acid plus a strong base, for example hydrochloric acid plus sodium hydroxide, you're going to get a salt and water, and a salt and water are both neutral. So when they're exactly equal, your pH at the equivalence point is going to be 7. Now, when you're titrating, there's going to be a huge jump in pH at the equivalence point. And the equivalence point is exactly halfway up that huge jump, which we call the point of inflection. So here's an example of a titration curve that you will make when you titrate a strong acid with a strong base. In this case, it's hydrochloric acid plus sodium hydroxide. So we're starting with just acid. So we have acid, acid, acid. The pH is very low. And as we add sodium hydroxide, the pH starts to go up. And all of a sudden, there's this huge jump. And this huge jump is where the equivalence point is located. So halfway up that jump is the equivalence point, the point of inflection, and from there on our pH starts to turn basic because now we have more base being added than there is acid. So again, the pH is going to be equal to 7 at the equivalence point for a strong acid, strong base titration. And the point of inflection is the big jump in pH at the equivalence. So halfway up this point of inflection is the equivalence.